Okay, so we've looked at producing the action potential at the axon hillock. We've looked at how it travels, or how we get the information from the axon hillock down to the axon terminal. Now we have to look at the final thing, the release of the neurotransmitter. Okay, now that neurotransmitter gets released out into an area that we may call the synapse if it has an effect on another nerve cell. And this, for example, could be the dendrite of another nerve. So we're really coming back to where we started from, where we're producing a response in a nerve. And that's, remember, where we started back in the first video in part 1 of this. Alright, so let's go back to this. We know that the action potential, or we've produced an action potential here at the axon terminal. What does that do? Well, it depolarizes the membrane, and you find that on the membrane of the axon terminal you have many channels. And we have voltage-dependent calcium channels. Now the important thing here is that when the action potential reaches here and depolarizes the axon terminal, what it does is it opens up these voltage-dependent calcium channels, or the probability of them being opened. So we have voltage-dependent calcium channels, calcium concentration, high outside, low inside. So therefore, bam, calcium ions come rushing into the axon terminal, and you get an increase in intracellular calcium concentration in this axon terminal. Now what this does is this causes vesicles which contain neurotransmitters in the nerve terminal. These vesicles, just so you know, have been made all the way back up in the nerve cell body. They've been made usual way with the ribosomes, the Golgi apparatus and so on. So they've been made, packaged and sent down to be stored in the nerve terminal, ready for this point in time. Here is their time to go. So calcium ions come rushing in, cause the vesicles then to move. They move to the membrane of the axon terminal. They fuse with the membrane and then release their contents, the neurotransmitters, into the synaptic cleft, into this area here. So because it's such a small area, the neurotransmitter is very concentrated in this area. So because it's very concentrated in this area, it will bind to any receptors that are present that have the binding site for this neurotransmitter. And obviously if it's a nerve to another nerve and there's a synapse, there's going to be these receptors present. So the neurotransmitter gets released, binds to its receptor and produces whatever changes in this. And it can produce something like an EPSP, an excitatory postsynaptic potential that we looked about in that first lecture, or an inhibitory postsynaptic potential, okay, that we have also sort of just mentioned but not talked about too much. But we're jumping a little bit afar. So it gets released and binds to the receptor and causes the effect. So that's all good, and it's sort of very simplistic, but you also have to remember is you release it, but what then happens to the neurotransmitter once it gets released? It doesn't stay there forever, because if it stayed there forever it would continuously stimulate this nerve, and this isn't what we want. The whole thing about transmission is telling this nerve when we want it to do what we want it to do, if we want to excite it or inhibit it. So how do we turn this off? There's a couple of ways. One, the transmitter may be taken back up into the nerve terminal. It may be taken up into the postsynaptic terminal, or there may be enzymes present here in the synaptic cleft that will break down this neurotransmitter. So there's lots of different ways that you can decrease it. So therefore, the response of this postsynaptic cell is not forever. It's only very short term, for as long as the neurotransmitter stays in a high enough concentration. So if we want to maintain the response that we're trying to bring, be it stimulation or inhibition, what do we have to do? We have to continuously stimulate this nerve and send information down this nerve. And it's in this way that we control what's happening at this postsynaptic nerve. So in summary, depolarization, calcium comes flooding in, increasing calcium inside causes the vesicles to fuse, release their contents, and the neurotransmitter then binds to its receptor to cause whatever response we're seeing in the cell that we're transmitting our information to. I hope that's made things a little bit more clearer about what's going on there. Okay, I'll see you later.